Hello and welcome everybody. My name is I.Nitze and I'm here presenting my talk for this year's AGU towards a deep learning based inventory of retrogressive thaw slumps across the Arctic. So here we see some examples of nice retrogressive thaw slumps. They are abundant features in ice-rich permafrost, like formerly glaciated terrain or Jedoma permafrost. So they are very important because they are disturbances in permafrost. They influence biogeochemical cycles like the carbon cycle, hydrological cycles. They can force further disturbances in the surroundings. They are a potential geohazard. They are also important for downstream ecology, for subsistence, for example, fishing and fisheries, but they're also an important indicator of the climate change that we see in the Arctic. From a remote sensing perspective and from a mapping perspective, we have to understand that they are pretty dynamic features. So they're variable in size and shape. Their stratigraphy can be very different. The vegetation surrounding them can be also very different. So we have a lot of thaw slumps in tundra areas, but also in boreal areas. And they're pretty dynamic. And sometimes even their definition is not really clear. So what is a thaw slump? What belongs to it? What does not belong to it? And this massive variability makes it pretty tough to map them consistently. What we are trying here is to apply deep learning to map and monitor these features across large areas. And over the past years, we have a lot of new data and techniques that have become available. For example, data. So we have planet scope data, we have very high resolution data constellations, we have high resolution elevation models like the Arctic DM. But we have a lot of new methods, deep learning, machine learning, computer vision, all different sorts of applications. And of course, we have increasingly strong computational resources like GPU processing, high performance computing, cloud computing, etc. And this has spawned some new papers, although there are very few in permafrost research, and especially in thaw slumps. But for example, here from my colleague Ling Wang, who kind of started the deep learning analysis for mapping thaw slumps. Here, an example from Tibet. Last year, we already presented on kind of our first tests of methodology. So we are also applying deep learning on most planet data, but also auxiliary data like the Arctic DM. There we applied that, tested the methodology on 6 sites, did a cross-validation to test the transferability. And you can check the presentation, the online presentation here on YouTube. I uploaded it, so you can easily recall that if you like. But we did not only want to focus on these 6 areas, because that was more or less an initial test. We're focusing on something bigger. So we want to scale these data. We want to have a temporal monitoring. And as thaw slumps are not only 2-dimensional, then rather 3-dimensional. So we also want to have a volumetric analysis to better understand how much material is moved and what the consequences are. That's why we scaled our analysis up so far. So this is kind of an intermediate result. We had a planet scope quota of about 1 million square kilometers. We expanded our studies to these areas. These are kind of selected areas where we know that thaw slumps are happening or are very likely. We have over 3,000 planet images. At the moment, for upscaling, we use PlanetScope orthotiles because they're a bit easier to handle and better to organize. So we have about 850 unique tiles, and we have in total more than 4,000 training samples, so hand-digitized thaw slumps. And we use an iterative approach where we digitize, train a model, analyze the output, and repeat this process with retraining the model in new areas, analyze it, and look where it performs well. And then again, repeat that process again. So this is an example from Banks Island of our data. In the background, you see Esri satellite layer, and these are individual outlines of our model, what the model thinks. So we see a nice gradual expansion of this thaw slump, which gets covered here quite well. So we see a growing thaw slump, and in blue you see the 3D information of the elevation loss, which is calculated from tandem X data. We also have that in many other areas where it works quite well. Here on the left you see a thaw slump in the Peel Plateau, where you see a nice expansion of the thaw slump. So from white in 2018 to red in 2021. And on the right-hand side, you see the same also in Novaya Zemlya, which is in northwestern Russia. So these are the good examples. So we see good performance of our model in well-known regions, so close to where we trained the data. We see we can track the temporal evolution where we have good data. And also the head wall is pretty nicely defined. The lower parts are a bit trickier because there the definition is always sometimes a bit fuzzy. Okay, now we want to scale that to the Arctic. So the positives that we said were the good performance in trained areas. So that works quite well. It's a fast and established processing pipeline with good hardware and good pipeline that's easy to expand. But there are a lot of challenges. So we have many false positives. So, the spatial diversity is sometimes a bit tricky. Here in these figures, we see, for example, a meandering river where there's less vegetation, and these are often false positives of thaw slump detection. Sometimes water is a bit tricky, so that's kind of an issue. The second big issue are semantics. So, what is a thaw slump? There is a big ongoing community effort to clarify that, to provide good training data and also validation data, and data access for planet data is kind of limited because it's commercial data. Now I want to give you a little outlook what we are working on. So we're working on self-supervised learning, which is an approach that works with a very limited data set of training labels, so it looks on its own to improve without specifically designated training labels. Then use additional data sources like Sentinel-2. For example, we see here on the left Planet and on the right-hand side Sentinel-2. So on big thaw slumps, we see that the information is rather similar. We can scale it better to a pan-Arctic extent, and we can apply a monitoring approach because the data are freely available. And as a third one, we want to track volumetric changes. So thaw slumps are 3D features. Having that information in the end is then very valuable. And I thank you for listening to this quite short talk. You can ask questions if you like. You can send me an email. You can check out social media. And also the code for this project is available. Training labels are available. And last year's part is also published as a paper. And I thank you, and I'm open for questions. Thank you.